Let's talk about tangent planes and normal lines of a surface. So here we're given a two-variable function, and the graph of a two-variable function will be a surface, right? Because you're thinking of the value of the function as the height. So here's x, here's y, and each point, if you plug into this function, it will give you some height. It's not so easy to think about the level curves of this. Let me do my best approach to this, best effort to find the level curves, but it's not the important part of this lecture, okay? So if I say k equals to 1, you get x squared times y equals to 1. That means y equals to 1 over x squared. What kind of graph is that? That's if you put something that's okay. So if you plug in 1 or negative 1, you get 1. Now, if you plug in something less than 1, what happens to the y? Does it become big or small? Say if you plug in 1/2, what do you get? 1/2 squared is 1/4. If you divide 1 by 1/4, 4. Positive 4. So at 1/2, you get some 4, which is a big value. Right? Same thing happens if you plug in negative 1/2. You also get positive. And the smaller you go, the smaller the x gets, the bigger the y is going to go. So it's going to shoot up like that. On the other hand, the bigger the x gets, what happens to y? The smaller it gets. So it just keeps decreasing. Does it ever become negative? No, it's always like this. So this is going to be k equals to 1. Okay? What if k is 2? Then you have x squared y equals to 2, so y is equal to 2 over x squared. That's basically same as this one. You just multiply by 2, so everything is, you're taking this graph and you're multiplying the y value by 2. That's what this is doing, right? So you just have the same kind of graph that's taller. So that's going to be your k equals to 2. And then you can kind of imagine what's going to happen as k equals to 3, and then 4, like that, okay? A tricky thing happens when k is 0. If k is 0, then you're talking about x squared y being equal to 0, the z value being equal to 0. What's the graph of this? Okay, so what kind of lines do you get? You get the x-axis and the y-axis, right? Yeah. So the graph of this is going to be the y-axis itself and the x-axis itself. K equals to 0. And the reason for that is, if you think about what a graph is a set of x-y pair values that makes this work, right? But if something multiplied to 0, we know that it's either x squared equal to 0 or y equals to 0, right? And that happens when x is 0 and y is 0. What does that give you? X-axis or y-axis? The y-axis. Okay, how about this one? The x-axis. Okay, so you get the two axes. In other words, anything that looks like 0, 1, I know is going to satisfy this. Why? Because x is 0. 0 times anything is 0. So it could be 0, 4, 0, 11, would you name it? 0, anything is always a solution of this. So the 0, anything means every point on the y-axis will satisfy this equation. So that's on the graph. Okay? Everything on the x-axis will also satisfy the equation. So you end up with two lines at k equals 0. Okay, now think about k equals to negative 1. You get x squared y equals to negative 1. And if you solve for y, you get negative 1 over x squared. And that's like taking the original graph at 1 over x squared and you're flipping it upside down, right? So if you flip it upside down, that's what you get. So the idea of the level curves are like, you have this thing, which is k equals to 1, and then goes, as you go further in that direction or that direction, the altitude goes up, right? Here's the sea level. This is k equals to 0. 2, 3. And then here's the sea. So you're below the sea level. Okay? The altitude is negative, so you're below the sea level. Looks like that. It's hard to picture, but it seems like, so imagine that you're a person that lives on this terrain. Then if you are walking alongside, you're there, you're exactly at the sea level, which means that you're at the beach. Okay, so there's like a beach here, beach there, but then once you go slightly to this side or that side, the waters are there, right? And if you go this way, there's a mountain, and this way there's another mountain that way. So can you picture it? Okay, good. And in this terrain, you're at location negative 2, 1, 4. So negative 2, 1 is somewhere here. Actually, it's, all right, sorry, this is more like 4, and then this should be something higher, I don't know, 8 or something, yeah. So if you're here, it's still going to be 4, no, it'll be negative 2, 1 for x and y, but then the altitude above here will be 4. That's where you are. And think about that shape. So I don't know how to draw that shape, but it's some kind of surface here. And the question is asking us to find the tangent plane to the surface. So if you have some kind of a surface, we're looking for some plane that's tangent to that point. Let's say this is 2, 1. Here's like negative 2. Here's x direction, and that's like y direction. Here's 1, and then up it's like this 4. So that's like the place where you are. So there's like some surface, and then you're trying to find the equation of the plane. Now, this could be just a separate question about drawing the level curves of this function, okay? So that's what I spent, but when the question is just to find the equation of tangent plane, you don't have to do all this work. All you care is that, oh, the graph will be some surface. That's all you care, okay? Now, to get a plane in 3D, what are the things that you need? What do you need in order to build a plane equation?
A, B, and C, and a point.
Right, so the plane equation is A, x minus x1 plus B, y minus y1 plus C, z minus z1 equals to 0. Okay? And what's the meaning of x1, y1, z1? This is a point on the plane. On the plane. Point on the plane. What's the meaning of A and C?
It's the direction of the plane.
No, you don't say it's the direction.
What's the normal vector?
Normal vector to the plane. Thank you. Now we already have a point. What's that? We're already given a point. What? Negative 2, 1, 4 is the point on the surface where the tangent plane must be touching. So the tangent plane should also pass through this point. So we have a point. That's something that we already have. That means the only thing that we have to figure out is what is this normal vector? That's the question. That's all. Once you figure that out, then you can answer this. The problem is we haven't learned anything that we haven't learned anything that would give us the normal vector to a surface, except just one place. Would you know when we did like something that's normal to a surface? What's normal to a surface?
How is it made a cross product?
And that's a good intuition. Of course, like if you want to have a normal vector for a plane, often you take two vectors inside the plane and you do a cross product, gives you the normal direction. But unfortunately here, you don't have any vectors to play with and you would know that it's inside the plane, so that's not going to help. So this is really hard to think, but the idea, the core idea is gradient. Oh, I shouldn't say gradient of F. I'll just say gradient. This has a potential to be very misleading, so you have to be careful. I'll talk about that. So gradient is perpendicular to what? Gradient is perpendicular to? Come on, we just learned that. You know.
Oh, so curves.
Yeah, level curves, but that's not going to help us. But we also learned that gradient is perpendicular to level surfaces when? In 3D, right? So if you have a 3-variable function, then the level surfaces, you don't have level curves, instead you have level surfaces. And gradient is perpendicular to those level surfaces. Okay. So what we do is we have to think about the surface as a 3-variable function, not a 2-variable function. Okay. In order to use that idea, you have to change this into so to use the above, we need a 3-variable function. Okay. So what we do is we first write this as z equals to x squared y. And that's a start, right? I recognize that when you draw the graph, you're really thinking of the value of this function as z. That's what you do, okay? Then you move this to the other side and you rewrite this as 0 equals to x squared y minus z. Do you see where I'm going with this? What's my new 3-variable function? X squared y minus z. That's going to be a 3-variable function, right? So if you say capital F is fxy minus z, which is, in our case, x squared y minus z, right? Then, what's the k equal to 0 level curve? K equals to 0 level curve is this one, right? Level surface, not curve. Okay. So this is a 3-variable function, so its level something is a surface. Actually, so this is a level surface with k equals to 0, which then means if I take the gradient of this function, that's going to be perpendicular to this. Okay. So again, going back to what I said, this is highly misleading. Is misleading because when you just hear the idea, then you immediately go to this function and say, hey, that's what I need to do, right? But this is not what we want. Instead, we have to use gradient of capital F, right? What's this capital F? You just subtract off of z and you get a, you write it as z equals to that function and then you move this to the other side so you get that, and that's what it is, okay? Okay, so let's now calculate gradient of f, capital F, which is if I differentiate this by x, this is as 2xy. If I differentiate this by y, I get x squared, right? Is that it? No, because f is a 3-variable function. What's the gradient? You just calculate all possible derivatives, right? So what's next? Comma.
X squared y minus 1.
Yeah, these are both constants when you do a partial derivative with respect to z, right? So you just get -1.
Oh, okay.
Yeah, so this is capital F, this function differentiated with respect to x. This is this function differentiated with respect to y. This -1 is this function differentiated with respect to z. Yes.
We're doing 3 variables because we're looking at a plane, not.
Because we're doing 3 variables because we need a normal vector in space, but we learned that gradient is perpendicular to level surfaces. Only in 3D. In 2D, that's not true. In 2D, gradients are perpendicular to level curves. We can't use that. We want something that's perpendicular to surface, not a curve. Okay, so we take we introduce a z and move the z to the other side, and now we have that. Okay? Yeah. So that's a little confusing. Now, because of that, a lot of textbooks just have a separate formula for the tangent surface, but I highly despise approaches like that. I really think Calculus 3 should be more conceptual than other ones because it's the conceptual understanding of Calc 3 that's more beneficial in your other classes, not just how to calculate, okay? You know, Calc 1 and 2, those calculation techniques used in so many places, it's good to just practice after practice, but in Calc 3, you want to be more conceptual, okay? All right, so this is what you have, but we're not done yet because we need the gradient of f at this point, -2, 1, 4. So that means x is -2, y is 1, and z is 4. So we have to plug in those values. So 2 times x is -2. So 2 times -2, y is 1, and then -2 squared, and -1. Notice that z value 4 actually doesn't get used at all because the gradient formula doesn't have any z. Z, when you differentiate it, just goes away, right? It becomes -1. Okay, so that gives us -4, +4, -1. Perfect. That's going to be our normal vector because that's the gradient, which is normal to the level surfaces. And we're ready to write down the answer now, right? What's the answer? Answer is -4 times x minus something, +4 times x minus y minus something, and then -1 z minus something equals to 0. So I just took these vectors and placed it as the coefficients. That's where the normal vector goes in. For these, you have to use this one, right? -2, 1, and 4. So minus -2 is +2, -1, -4. So that's going to be your answer. Any questions?